Hello everybody, welcome back to this channel. Today we're going to talk about the response to any input, and different from the way we did before, we're going to look at the convolution integral, which is very special, and sometimes this could become a very difficult point. So I'm going to have 4 video clips, 3 for the convolution and 1 for the network design. Network design is different from what we have been doing for the analysis. And network design is come up with the circuits that that actually satisfy a certain transfer function or network function. So, as always, I'm gonna put the link to the Google Colab notes in the description down below. And actually, I created a list of all the files, so that link including all the files on the page. So if you have any question, feel free to leave comments, and let's get started. And so so we looking at the impulse response and also the step response, right? So what if you have any type of response? So the xt is the input, and you can do this by integrate with the FHT is the impulse response. So in this case, we know the impulse response in time, and actually you can calculate the output without really doing the Laplace transform and then do the inverse Laplace transform. You can do this. This is called convolution integral. And this integral is you replace ht by ht minus tau and x tau, and you integrate with respect to tau. Okay, and so the first clip will look at why this is correct. Okay, and then there's short hand notation for this, just ht asterisk xt. This is not the times, this is not multiplication. Instead, this means the ht convolved with xt. Okay, so let's see why this is correct. So let's start with the Laplace transform. In the Laplace domain, ys should be equal to ts times xs, right? And since ts is also equal to hs times xs. The xs is just the Laplace transform of xt, right? So I can write the Laplace transform 0 to infinity xt e to minus st dt. In fact, I would like to use a tau as a dummy variable. The dummy variable could be anything, just to be consistent with the form we're trying to get. Okay, so I have x tau here. So everything, this is just the definition of Laplace transform, right? This is just the Laplace transform of xt, and and now the ys is just, if I substitute this back to this equation, to hs there, to this equation here, and in this case we will have hs times 0 to infinity x tau. I'm going a little bit more in detailed steps. I'm not skipping the steps. So in this case, since the integral is with respect to tau, and hs is the function of s, so I can move this hs inside this integral, and without really changing anything. And also I move this st, switch the position of e to minus s tau and x tau d tau. So this is the integration. We didn't do much on this yet. And one thing we want to recognize that is the S domain, the time domain translation property. The time domain is the basic delay. Time domain translation property of the Laplace transform and we have Hs and Hs times the E2 minus S tau, and this actually is equal the Laplace transform of Ht minus tau is a delay, right? So Hs is a Laplace transform of Ht, and Ht minus tau, and we also need to multiply that by ut minus tau. So we basically the Ht delayed by tau, and then E2 minus St dt. So that's based on the time domain translation property, right? And now I want substitute this back into the Ys. So the equation become a little bit long here. Let's see, 0 to infinity. I just want to go write this integral here, 0 ht minus tau and ut minus tau and e2 minus st dt. And you see the reason why I use one use tau, the other use t, so that we don't get confused. And so this term here, I just wrote here, is just the hs times the e2 minus s tau, right? And then I need to have the rest s tau and d tau. So now I have two integrals. One is inner one, and the other one is outside. So the inside, we're trying to see if we can switch this. If we can switch, then we can recognize what the yt inside that dt. That's where I'm going. And what I'm doing here is I can, since the inner integral is with respect to time t, and I can move x tau inside, right? So this one is going to be equal 0 to infinity, and the inner one 0 to infinity, ht minus tau, and ut minus tau, and I have e2 minus st and x tau, and then I integrate with respect to dt and with respect to tau. Now, since this integration, this double integral here, I can switch the sequence, which variable I first integrate. I can first integrate tau instead of t. So the next step, I switch the integration sequence. Nothing, the integrand doesn't change. T minus tau and ut minus tau and e2 minus st and x tau. I first integrate with respect to tau and then integrate with respect to t. And if we look at inside the inner integral now is with respect to tau, since this term e2 minus st has nothing to do with tau, so I can move that outside. So I will move that to 0 to the outer integral. I'm left with inside the integrand for the inner integral ut minus tau times x tau d tau, and move e2 minus st outside. Okay, and then I would like to work this a little bit. This is very close to the final format we're trying to have, and so in this case this is equal to, since ut minus tau, we integrate over tau, right? The tau goes from 0 to t once. Tau is greater than t, so this ut, this one here, it becomes 0 if tau is greater than t. So the upper limit, I don't really have to integrate all the way to the infinity. Instead, I put the upper limit as a t. So in that case, in this interval from 0 to t, actually ut is equal to 1. So in this case, I can just drop that one, ht minus tau, x tau, d tau. So this is the inner integral, and times e2 minus st dt. Now, so this is the ys. And we also know ys is the Laplace transform of yt, which is equal to 0 to infinity yt e2 minus st dt. If we compare this, and we find this one here is the term in front of e2 minus st, this should be yt, right? So that's the reason the yt is equal to 0 to t ht minus tau x tau d tau. So this is the most commonly used term, used form in the convolution integral. But it also equivalently, this is also true, yt is also true if you do similar derivation. That's also true h tau and xt minus tau d tau. So you can do either way, will be fine. But this one is the most commonly used way. Okay, and the physical sort of the graphical interpretation is more meaningful for this form. So we're gonna choose this form. Okay, so in the next clip we're gonna look at an example how we actually carry out this convolution integral. Okay, I'll see you in a moment.